All right, well, this is 6.3, Redox Reactions and Electrochemical Cells. This can be covered in pages 671 through 695 in your textbook and page 281 to 294 in your study guide. Also, I want you to make sure that you see the note that I left for you on Canvas regarding the reading. All right. So redox reactions, we're going to be talking about those. Those involve electron transfer from one element to another in a reaction. Now, we just talked about the different types of reactions. So on your redox reactions, these typically involve the synthesis reactions, decomposition reactions, single replacement reactions, and combustion reactions. So it involves the reactions that have a element at some point in the reaction that is by itself, usually, that the charge of that element is going to change. And we'll talk more about that here. So with redox reactions, we have to look at what's called oxidation states. So pause the video and write these down, and then we'll talk about it. All right, so when we're doing oxidation states, these are some rules. Atoms that are in elements, in elemental form, which means they're standalone elements, have an oxidation of 0. So say, for example, you have I2 plus O2 yields 2IO. Well, this is an elemental form, okay? It's a diatomic element, it's an elemental form, so its oxidation state is going to be 0. You can kind of think of oxidation states as charges because they're almost the same with few exceptions, okay? So monatomic ions get their ionic form. So what that means is if you see an element, say, for example, in an equation where you have like hydrogen plus something else here yields something else here. All right, so this is a monatomic ion. It's in its ionic form, and it tells you the charge here. So it gets its ionic charge. So this is going to be a +1 for an oxidation number. Okay? All right, so the third one, oxygen always is a -2, except when it's in peroxide where they're a -1. So like hydrogen peroxide, H2O2. All right, this is the polyatomic ion peroxide. So here it's going to be a -1. Here the hydrogen's going to be a +1. But for example, when it's in water, this is not a peroxide, this is oxygen, so it's going to be a -2. All right. Now, also you'll see sometimes oxygen in a case where it's not the second element, it's the first element, like we see here. Well, in this case, the more electronegative element is going to get its most common charge. So if we look at fluorine on the periodic table, it's in the halogens, it's a -1. So since we have 2 of these, the overall charge here of the negative side of this is -2. So that means that this oxygen must be a +2 to counter, because these, remember, have to always be neutral. Hydrogen is always a +1, except in metal hydrides where they're a -1, like HS, okay, HS. This is a -2. Well, that's not a metal hydride. I can't think of one right now, but when we get to this case, I will show you if there's one in the examples. Oxidation states in compounds must sum to zero. That's what we've been talking about all along. Oxidation states in polyatomic ions must sum to the ionic charge. So let's look at a polyatomic ion, SO3. Okay, so remember the polyatomic ion SO3. Let's look at the polyatomic ion list again. Now, if you don't have this at home, I am going to put this in Canvas so that you can get this. So, and you can have these. So let's go to our home page. All right, reference materials, it's going to be right here. You just click on reference materials and it's going to bring up all of your reference materials. And you can go ahead and either save this to your computer or you can print it out. All right, so SO3 is a sulfate. Let's find the, oh no, it's SO, that's a sulfite. So SO3 sulfite is a -2 charge. All right, so when we're doing this, we have a -2 for oxygen here. So that makes the negative side of this -6. Well, if we have to have an overall charge of -2, then the sulfur here has to be +4, because this +4 will neutralize 4 of these negatives, leaving 2 negatives left over. So it has to sum to its ionic charge. All right, so the next rule, always assign the more electronegative element a negative oxidation number. That's what we did here. So since fluorine is more electronegative, it gets its negative oxidation number, which makes the oxygen then a +2. In a compound or ion containing more than 2 elements, the element on the right side takes the most common oxidation state. Okay, so if we had H2SO4, all right, so this is a compound or ion containing more than 2 elements. It actually contains 3 elements. It says the element on the right takes the most common oxidation state. So that would be the oxygen. So the oxygen is going to take the most common oxidation state, which is going to be a -2. Hydrogen's always a +1. We have that roll here. Okay, this is not a metal hydride. This is an acid. So that leaves us trying to figure out what the sulfur is going to be. So if we have -2 times 4 is a -8. We have 2 hydrogens here that give us a +1, so that's a +2. Well, in order to make this sum to 0, then we have to have the sulfur as a +6 charge. So you see, that's how you do it if you have more than 2 elements. All right, so let's put this into practice and let's do some redox equations. So pause the video and write down these steps for doing a redox equation. All right, so the first thing that we want to do is write the full balanced chemical equation. So it says here that magnesium metal, right here, is burned in the presence of oxygen, O2, to form magnesium oxide, MgO. All right, so what we want to do is balance this first. So we don't have these two. So this O2 here requires us to put a 2 coefficient here so that we have 2 oxygens. So we have 2 magnesiums, so now we have to come over here and put a 2 in front of magnesium to have 2 magnesiums. Okay, so the next step is to assign oxidation numbers. So for your magnesium here, it's a 0 because this is an element that is alone by itself, and that's number 1 rule here. Atoms in elemental form, standalone elements, have an oxidation number of 0. Same thing here with oxygen, diatomic oxygen, it's standalone, so it gets 0. Now over here in the compound, it's not standalone, so the element oxygen has a -2 charge, so that's its oxidation number. So since this has to sum to 0, the magnesium has to be a +2. All right, so let's analyze what's happening here. Magnesium is going from a 0 charge here, I'm going to write 0 above it, to a +2 here. How does it do that? Well, magnesium has got to lose 2 electrons. So in order for this equation to balance out, we have to have 2 electrons, that magnesium, on this side. Now, since there's 2 atoms of magnesium, we have to multiply the number of electrons by 2. So that's how we get 4 electrons here. So in order to balance these charges here, we have to add 4 electrons. Now, I said that you have to make sure that the electrons balance. So if this is a +2, then we have to take these 2 electrons. They have to be separate, so that's why we added it to this side. All right, and then so for the oxygen, we have the oxidation number of 0 here. Over here, it's a -2. So I have that right there. I already wrote it. So in order for this to go from a 0 to a -2, we've got to add 4 electrons on this side. Now it's 2, so that makes it -4. So what you're going to do is you're going to look at these these are called half equations. This is the half equation for magnesium. This is the half equation for oxygen. And what you're going to see is you're going to have the same number of electrons on this side as you have on this side. You should, so that they'll cancel out. Okay. All right. So let's look at another one. Okay. So here are the steps again. So we're going to write the products of this equation. So sodium is going to kick out silver. So we're going to have sodium chloride plus silver. Okay. Now, how can we verify that that reaction is actually going to happen? What we're going to have to do is we're going to have to look at our activity series. So sodium is right here, and silver is way down here at the bottom. So sodium is stronger than silver. The higher up, remember, the higher up on the activity series, the stronger it is. If this element is stronger than this element, it's going to push it out. Okay, so sodium is going to push out silver and bond with the chlorine, and then silver is going to be kicked out by itself. All right, so we want to assign oxidation numbers. So chlorine's a -1. That means silver is a +1. This is a standalone element, so it's 0. All right, so here we have chlorine's a -1. That must mean sodium's a +1. And here we have silver standing alone, so its oxidation number is 0. Okay, so let's take the half equations. We have silver on this side. That is going to silver 0. It's +1 here, and it's 0 here. So how did this happen? Well, in order for it to go from a +1 to a 0, this one has to neutralize this positive charge. So how can it neutralize that positive charge? By adding an electron here. So this side equals, that's what the arrow means, this side. So if we have silver +1 electron, it is going to equal silver with a 0 charge, or oxidation state. All right. Oh, we forgot to balance our equation. Ag, Cl, Cl, Na, Na. NaCl +1, -1, so we don't have any subscripts here. So we're all good. We didn't have to add any coefficients to balance this. All right, so let's look at sodium. We have sodium here. That is a 0 oxidation state, and it's going to a sodium here that's got a +1. So how does this happen? How do we get from 0 to +1? Well, this has got to lose an electron. This one has to take an electron off. Okay, I'm sorry, you have to add an electron to this side to get here. So if you look, these two sides equal. So we have sodium plus an electron here is equal to sodium 0. We have an electron on this side, and we have one electron on this side. So this balances out. Now the chlorine doesn't change its oxidation number, so we don't have to worry about that. That's more like a spectator ion. It doesn't change. We're just looking at what changes its oxidation number. All right, so here is a page that's really important. So go ahead and pause the video and write this down. This is summing up everything that we've talked about to this point. All right, so redox, oxidation is losing electrons. So if you have and here is the silver and the sodium, the half reactions that we just wrote. If you have an element that is losing electrons, that is called oxidation. And when an element gains electrons, that is called reduction. So here we have silver that's gaining an electron to become silver with no charge. So a silver ion gaining an electron is silver with no charge. So since this is gaining an electron, silver is being reduced. Okay, and here we have sodium. Sodium is losing an electron. So we go from sodium here to sodium plus an electron. So this is oxidation. So oxidation is losing electrons, reduction is gaining electrons. All right, so let's fill in these blanks here. Oxidation, the element is losing electrons. And in reduction, the element is gaining electrons. Okay, so since this is gaining electrons, let's look at its charge. Its charge is becoming more negative. And in oxidation, the element is becoming more positive. All right. So for oxidation, in the half reaction, the electron is we're looking for a product or reactant. So let's look at oxidation. Right here is oxidation. Where's the electron? The electron is a product. Okay, and in reduction, the electron is a reactant. Oops, I forgot my C. Sorry, little c. All right. Make sure that you understand this page here fully before we go on. All right, now sometimes in a single replacement equations, these are called push-out equations, like I mentioned a while ago. It's not the positive, it's not the metals that are changing. Sometimes it's the halogens that are changing. Okay, so if we look at this equation where we have lithium plus sodium chloride, these are the negative, okay? I'm sorry, the lithium is, let's see, positive, positive. This is the normal type of equation. So let's look back at our periodic table. So here's lithium. Lithium is positive and sodium is positive. So these two are both positive. So that's what we've been talking about in our normal single replacement equations. So if we go back here, we're looking for lithium and sodium on our activity series. Lithium is at the top here, and sodium is here. So lithium is stronger. So lithium is going to push out sodium. So we're going to get lithium chloride plus sodium. And this is the type that we've been talking about where we have metals. But sometimes in this equation here, we have nonmetals. See, we have chlorine, which is a -1, and then we have fluorine, which is also an halogen. It's a negative charge. Okay, so fluorine and chlorine here. So the way we decide if this reaction is happening is by looking at electronegativity. The most electronegative element is stronger. So if we remember electronegativity, fluorine is the most electronegative element. So fluorine is stronger than chlorine, is stronger than bromine, is stronger than iodine. So that's what this is referring to right here. Fluorine is stronger, greater than chlorine, which is stronger than bromine, which is stronger than iodine. So here, since fluorine is stronger than chlorine, then the sodium is going to have to bond with the fluorine, and it's going to kick chlorine out. So that's the way we decide if these reactions where the two halogens are fighting for the getting to bond with the sodium. Okay, that's just a little side note if you ever have that situation. Okay, so for this, we're going to balance our redox equation in an acidic or basic solution. This is on page 442 of book 2. It goes through this explanation if you want to look over that and see that. All right, so for this first one, we're going to balance this reaction in an acidic solution. Now remember, acidic solutions contain hydrogen ions, and basic solutions contain hydroxide ions. So when we end up here with this final answer, it's going to have H plus because it's in an acidic solution. So we'll see that. Let's see if it all works out. All right, so my first step is to separate these into two half equations because I see I have IO3 -1 and iodine over here. So what you want to do is you want to keep elements that are alike together. So I have IO3 plus, I'm sorry, not plus, yields I2 on this side. Okay, and so for this half equation, I'm going to have HSO3, the negative, going to SO4, -2. All right, so I kept these together and I kept these together in my half equation. So I'm going to draw a little line here. Okay, so let's work with this side first. So what we want to do is we want to balance everything except hydrogen and oxygen first. So we have one I here, we have two I's here, so I'm going to need two of these to balance off the iodine. Now, we have oxygen on this side, but we don't have any oxygen on this side, and we're going to have to fix that. Now, when you're balancing these in acidic or basic solutions, the way that you fix that is you want to fix look at the oxygen, you want to fix the oxygen with water. So we're going to add some water on this side, H2O. Now, we have 3 oxygens here, but we have 2 of them, so 2 times 3 is 6, so we're going to have to put a 6 here in front to make 6 oxygen. Now we have hydrogen on this side where we don't have hydrogen on this side, so we're going to have to fix that. 6 times 2 is 12, so we're going to have to add 12 hydrogen over on this side. All right, so now we have everything balanced, 12 hydrogen, 2 iodine, 2 iodine, 6 oxygen, 6 oxygen. Okay, now I want to do the same thing to the other side. HSO3 to SO4, -2. Well, we have 1 sulfur here, 1 sulfur here, so we're good. So we want to equalize the oxygens by adding water. So if we have 3 oxygens here and 4 oxygens here, we want to add water to this side. So I'm going to have H2O plus HSO3 And this is going to yield SO4. Now that the oxygens are fixed, we have 4 oxygens, we need to fix the hydrogen. So we're going to need to add hydrogen to this side. Well, how many? Well, we have 2 plus 1 is 3 hydrogen added to this side. All right, so let's double check this to make sure it's correct. 2 plus 1 is 3 hydrogen, 3 hydrogen. O plus 3O, that's 4 O's. So we have 4 oxygens here, and then 1 sulfur, 1 sulfur. All right, so now these 2 half equations have been balanced. So now what we're going to do is we're going to look at the oxidation numbers. Well, hydrogen is always a plus 1. All right, so over here you want to do the right side first. So oxygen gets the most common oxidation number. That's going to be a -2. But we have 3 of them, so that's a -6. But this has to end up having a negative charge. So if this side's -6, and we want to have a -1 charge, the iodine here is +5. Over on this side, the iodine is by itself, so it's going to have a 0 oxidation number. Oxygen's -2. Hydrogen is a +1. Okay, so now what's changing? Well, hydrogen's staying at +1, oxygen's staying at +2, but the iodine is changing. We have a +5 here and a 0 here. So how does that happen? How do we get this from a +5 to a 0? We're going to have to add electrons. So which side? Well, if this is a +5 and this is a 0, we need to add negative charges to the reactant side. So +5 to 0, we need to add, and this is a negative, oh, but that doesn't matter. Okay, so +5 to 0, we need to add 5 electrons to this side. Okay, but how many iodine do we have? We have 2 iodine. So if each one is a +5, that must mean the total number of electrons is going to be 10. All right, so adding 10 electrons to this side is going to fix 2 iodines on this side to a 0. Looks like a C. Let me fix that. There you go. All right, so this side has been fixed with the number of electrons. Let's fix this side. All right, so oxygen's a -2, hydrogen +1. -2 plus 1. So we need to find out what the sulfur is going to be. So we have to have a negative charge here. So 2 times 3 is -6. But we already have a +1, so that's a -5. -5, but we want, so this is going to be a +4. Okay, so let's check that again. 6 here, 4 and 1 is 5, which means it leaves a negative. All right, so hydrogen is a +1, that doesn't change. Oxygen's a -2. 2 times 4 is -8. We want to end up with a -2 charge. So that must means this is a +4. Okay, so 6, 8, -2. All right, so sulfur here is changing from a +4 to a +6. Okay, so how does that happen? This has to equal. So if we have a +4 here and a +6 here, we need to add electrons to this side. Okay, how many? Well, 4 and 6, that must means we add 2 electrons. And there's only 1 sulfur, so that's 2 electrons. Now, the thing about oxidation and reduction is eventually this number of electrons has to be the same number as this electrons. So we're going to have to do something because this is 10 electrons and this is 2 electrons. So we're going to have to fix that. So the way that we fix that is just like in your combustion, where you multiply everything on one side by a certain number. We're going to do the same thing here. So how do we get 2 to 10? That must means we have to multiply everything by 5. Okay, so let's do that. So we're going to have 5H2O plus 5HSO3, that's a -1, yields 5SO4 at a -2 plus 15 hydrogens plus 10 electrons. All right, so now we have the electrons balanced out. So what we're going to do is now we're going to combine these two half reactions back together into a final reaction. So I'm just going to rewrite everything again right here. So 12 hydrogens plus 2 IO3s negative yields I2 plus 6 H2O. Okay, and under that I'm going to write the other half equation, 5 H2O plus 5 HSO3 -1 yields, I'm going to keep the yield signs lined up, 5 SO4 -2 plus 15 hydrogens plus 10 electrons. All right, so we're going to add these two back together. But before we do that, we want to eliminate things that are alike on this side and this side. So looking, the first thing that, I forgot to add the 10 electrons here. The first thing that's the same are the 10 electrons. So I can cross the 10 electrons out here. And the other thing that's going to be the same are the waters. If we have 6 waters here and 5 waters here, well, these 5 can neutralize 5 of them over here. So I'm just going to cross this out to leave 1 water here. All right, now the next thing that we can cross out are hydrogens. We have 12 hydrogens here. These 12 can neutralize 12 of these hydrogens. So 15 minus 12 is 3. So we have 3 hydrogens left on this side. So now remember, this is in an acidic solution. So it makes sense that we do have some hydrogen ions left over in this solution. So we're going to add these two back together. So what do we have on this side? We have 5 HSO3s plus 2 IO3s yields, okay, I2 plus H2O plus 5, SO4s, -2. My pen is acting up, sorry. Where was I? Plus 3 hydrogen ions. All right, so the final equation is 5 SO3 negatives plus 2 IO3 negative yields I2 plus H2O plus 5 SO4 -2 plus 3 hydrogen ions. This is going to be your final answer. All right, so if you're looking on page 4 or whatever page this is, or somewhere around 442 of book 2, and you see this example, you're going to see this, except for maybe some of these are going to be in different places, and that's okay. As long as you have all of this on the product side and all of this on the reactant side, it doesn't matter if this is over here and this is over here. That's like saying, what's 2 plus 3? It's equal to 5, right? Well, let's break down 5 again. 2 plus 3 is equal to 4 plus 1. Okay, or we could say, we could switch these places. 3 plus 2 is equal to 4 plus 1, right? That's the same. Or we could say 3 plus 2 is equal to 1 plus 4. So it doesn't matter what position these are in, okay, because we're adding. So these can be in different positions as well. All right. The next example is balancing a reaction in a basic solution. So here we're just looking at balancing it in a basic solution. So remember, basic means OH negative. All right, so here we just have a half reaction. Okay? We don't have other things that we have to deal with. So we have I2 yields IO4 negative 1. So the first thing that we want to do is we want to balance everything except oxygen and hydrogen. So iodine here. So I2 here. So we need 2 here to make 2 iodine. Now we have 4 oxygen here. So in order to balance off oxygens, we have to add water. So we're going to add H2O here. Well, we have 4 oxygens, so we need 4 oxygens on this side to make that equal. And here we have 8 hydrogen, so we're going to come over here. We're going to add 8 hydrogen here to make that equal. Oh, excuse me. Sorry. We have 4 oxygen, but we have 2 moles of it. So that's 8 oxygen. So we have to have an 8 here to make 8 oxygen, which is going to mean 16 hydrogen here. You got to be very diligent. Do this very, very slowly and methodically, and go back and recheck your numbers, or you're going to make some little tiny mistakes like I did. Okay. So let's figure out the oxidation number and what's changed so we know where to add some electrons. So this is -2. This is +1. This is going to be 0. Here we have -2. That's -8. But we have a negative here. So this is going to be a +7. The iodine here is going to be a +7 to give this a negative charge. And of course, hydrogen is a plus there. All right, so how do we get from 0 to a +7? Okay, so 0 on this side, +7 on this side. That means that the electrons are going to have to be added to this side. Now, 2 of the 7s is going to be 14 electrons. Okay, so we're going to have to add 14 electrons to this side. All right, so remember, this is in a basic solution, so we want to neutralize all of these hydrogen ions here. Say this is in a basic solution, so we can't have any hydrogen ions here. So what we're going to have to do is neutralize those by adding hydroxide ions. So we're going to have to add 16 hydroxide ions to this side. And if we add 16 hydroxide ions to this side, we're also going to have to add them to this side. Okay? All right. So once we do that, we're going to get rid of all of these hydroxides on this side, are going to make 16 waters. So 16H plus 16OH is going to make 16 H2O. They're going to combine together to make water on this side. Okay, so now we can cancel out what we have the same on both sides. So here we have 8 waters that can cancel out with 8 waters here, leaving 8 here. Let's see. Is that all we can cancel? Okay, and so what we're going to do is rewrite our equation, make sure that it's in a basic solution. Let's check that. We have 16 OH here. Remember, OH is a basic solution, hydroxides, so we're good. So we're just going to rewrite this to get this cleaner looking. So we have 16 OH plus I2 yields 2 IO4 plus 14 electrons plus 8 H2O. Okay, that's going to be your final equation right here. All right. Okay, so standard reduction potentials. These equations, redox equations, the reason that we're covering these is because the most common use for these is in making batteries, or what's called an electrochemical cell or a voltaic cell. And you have, remember in class we got a standard reduction potential table that had a bunch of half reactions and the voltage, the charge between these reactions. I'm also going to put that, link that in with the video so that you can have that at home to print that out. Okay, and so when we're looking at the Srp table, chemicals in the left-hand column will only spontaneously, that means without any help, okay, take electrons from chemicals below them in the right-hand column. So bromine cannot take electrons from chlorine because chlorine is higher, but it can from silver. So spontaneously, these electrons, this one, bromine, is stronger than silver, so that's why that works. So let's look at electrochemical cells. Electricity is produced by the spontaneous transfer of electrons. Electrochemical cells are often referred to as voltaic cells. Okay, there's those words. I was going to write them for you, but they're here. Voltaic or galvanic cells. These cells are the most common application of redox equations. So let's look at a voltaic cell. You don't have to write all of this down. Let's just look at it, and I'll talk about it. All right. So in a electrochemical cell, a voltaic cell, you have two beakers that have solutions in them. You have two wires that are in these beakers, and they have to be different types of metal plates or metal probes or electrodes. Dissolved in this solution has to be some same type of ion as the metal. So if this isn't a piece of metal wire here, then you have to have a solution of something that contains magnesium ions. So magnesium sulfate is a compound that's soluble in water, so they're using magnesium sulfate in this beaker here. Now over in this beaker, we have a copper electrode. So we have to have, this solution has to have copper ions in it. So copper sulfate is what they're using over here. Copper sulfate is soluble, so it does dissolve. So we have copper ions in this beaker, and we have magnesium ions in this beaker. Now these two metal electrodes, okay, are immersed in these solutions, and they are connected by a wire. And you see here, this just has a voltmeter in between it so it can register the voltage. But you can see here that the wire goes in and comes out. So we could take this voltage meter out and just connect these wires. Okay, so we're going to look at our Srp table, and this is going to allow us to predict the direction of the electron flow. Okay, so remember, the higher it is on this list, the stronger it is, and it's going to spontaneously pull electrons away from the other one. All right, so we're looking here at magnesium going to magnesium 2. So magnesium going to magnesium 2 plus 2 electrons. So let's find that on our standard reduction potential Srp table. So let's see here. All right, here it is right here. Magnesium right here going to magnesium 2. All right, and so the other side is copper. Let's see, let me go back to here. Copper 2 going to copper no charge. Okay, so let's find that one. If magnesium is here, copper 2 is not below it, so it must mean it's above it. So I'm just going to keep magnesium at the bottom of the screen, and let's find copper. Here's copper 2 going to copper 1. Oh, here's copper 2 going to copper right here. So copper is stronger than magnesium. So the flow of electrons is going to go to the copper because the copper is the stronger. So the flow of electrons are going to go from the magnesium side to the copper side. Okay, now look real close. Right here it shows you in the voltage meter, the electrons are going in this way and out this way to the copper. All right, so that must means that this copper side is going to start gaining electrons. Okay, so it's going to be electrons building up on this side. Now, here comes the other part of the electrochemical or voltaic cell. The magnesium is losing electrons, so the magnesium is losing electrons. Oxidation is losing. Oil rig, oxidation is losing. Let me go back to that so I can show you that. Okay, oxidation is losing, reduction is gaining. So that's how you remember these. Oil rig, oxidation is losing, reduction is gaining. So if magnesium is losing electrons, then it means that that's being oxidized. The electrode where oxidation occurs is called the anode. Okay, so there's some vocabulary for you. So this is the anode. It says here magnesium anode. And the other side where reduction is occurring is called the cathode. So this is the copper cathode. We see that right here. All right, so this side is gaining electrons. Now, what's going to happen is this is going to build up a negative charge here. It's going to cause this battery to become what's called polarized, where you have a negative charges build up here and positive charges building up here. And so when it becomes polarized, it's going to die. And that's going to happen very quickly. So in order to prevent that and to make this battery last longer, what you're going to do is you're going to have a tube here that's filled with salt. So in this case, it's sodium chloride. Now in the bottom here, you want to put some porous material like cotton so that the liquid just doesn't rush out and the liquid sodium chloride stays in here separated from the magnesium sulfate and copper sulfate here. So what's going to happen is because this is having a negative buildup on this side, it's going to pull the positive ion from the salt this direction. So it's going to pull the sodium ions this direction. The sodium ions are going to neutralize these negative charges. Okay, and so that's going to make the battery last longer. And vice versa, the chlorine here is going to migrate this way. Okay, you're going to have a neutralization because this is going to be building up a positive charge. So the chlorine negative is going to neutralize the positive charge here. It's going to keep this battery flowing. Okay, so this is the oxidation. It's losing electrons. This is the reduction. It's gaining the electrons. All right, so let's look at another cell. All right, so here we have, in this electrochemical cell, we have a silver plate here, and we have a chromium plate here. Okay, so we have to have chromium ions on this side and silver ions on this side. We have to have some kind of solution, salt solution, in this salt bridge here, and these are connected by a wire. Okay, so we have all the components of a electrochemical cell. So it says, which electrode is the anode? All right, so let's go back and look. The anode is where oxidation occurs. So anode is where oxidation occurs. Oxidation. Okay, and we know oxidation is losing electrons. So we're going to have to figure out which side is losing electrons and which side is gaining electrons. So we're going to have to go to our standard reduction potential, and we're going to have to find silver and chromium. Well, here's silver and here's chromium. So silver is stronger than chromium. So silver is going to pull electrons toward it, away from chromium. Okay, so which electrode is the anode? Oxidation is losing electrons. The chromium is losing electrons. So the anode is going to be chromium. So this is the anode. This is the cathode. Okay. In which direction do the electrons flow in the wire? Well, we just established that. We just established that it's going to go from chromium to silver. From chromium to silver. And in which direction do the cations flow through the salt bridge? All right, so cations are positive. So in the salt bridge here, we have positive and negative. So the positive is going to flow towards wherever the negative buildup is. So if electrons are negative and electrons are flowing this way, we're going to have negative charges build up here. So the positive ions are going to have to flow in this direction. So it's going to flow towards the silver from the right of the salt bridge to the left. So from the right to the left. And so that's where we have the arrow here. Which electrode gains mass? Okay, so if we have negative electrons here, this positive silver ion is going to be attracted to that, to those negative charges. And so it's going to attach here. So the electrode that's going to gain mass is going to be the silver electrode. All right, pretty simple. Okay, determining the cell potential. So determining the voltage of the cell. So the way that you determine the voltage of the cell is that you look at the cell potentials on your Srp. So you're going to be looking at these numbers right here that are on the far right side. So here we're working this first example out for you. So in this example here, we have nickel going to nickel +2. So if we look at our Srp and find the nickel right here, nickel +2 to nickel no charge. Now, this says, though, that it's nickel going to nickel +2. So we have, where to go? Nickel going to nickel +2. So we're going in the opposite direction that this shows here. Well, this one going from left to right, nickel +2 to nickel, is a negative 0.26. You see this double-sided arrow here, this double direction arrow? That means that this can go in the opposite direction too. So if we're going from left to right is a negative 0.26, we want to go from right to left. That's the opposite direction. So this sign is opposite. So that's going to become a positive 0.26. So that's why you see this is a positive 0.26. Okay, so finding bromine So we want to have bromine 2 going to bromine -1. And you have to look very closely because some of these, for example, I know copper does, you want to make sure that you're getting the correct. So see here, this is copper 2 going to copper 1. Okay, so we want to make sure that we find the correct one. We want to go from bromine 2 to bromine -1. So where's bromine? Right here. Bromine 2 to bromine -1. And we see that that is a plus 1.09. So 1.09 plus here. So what you want to do is you want to get these two values and then add them up. And that's going to be a 1.35. Okay? All right, so let's look at this one. This is the answer. We should end up with 2.0. So let's find aluminum going to aluminum +3 on our SRP. So aluminum, where's aluminum? Here it is. Aluminum +3 to aluminum. Okay, so what do we want? We want aluminum going to aluminum +3. So we want, where is it? Aluminum going to aluminum +3. So it's going from right to left in this direction. So this is a negative 1.66. We want the positive 1.66. All right, and we want copper 2 going to copper neutral. Now, be very careful. Copper 2 going to copper neutral. I saw that up here. All right, so this is copper 1 going to copper neutral. We want copper 2 going to copper neutral. Copper 2, right here, copper 2 going to copper 1. We don't want that. We want copper 2 going to copper neutral. Okay, so that's a 0.34. Okay, so we want to add those two together. So let's see here. So 1.66 plus, oh, I did it up here, 0.34. Okay, so we get 2.0. All right, so 2.0 is the correct answer that we wanted. All right. So it matched our answer here. So let's do this one. We want I -1 to I2. Oops. Right here. I -1 to I2. All right. -1 to I2. This is just balanced. Okay. So that shows a plus 0.54, but we're going from -1 to I2. So we want a negative 0.54 here. Negative 0.54. And then we have gold +3 to gold neutral. Gold +3. Right here. Gold +3 to gold neutral. That's a 1.50. So 1.50. So we want to add these up. 1.5 minus 0.54. 1.5 minus a 0.54. We get 9.6 times 10 to the -1. All right, so remember, 10 to the -1, we're going to take this decimal and we're going to move it one place to the left because this is negative, so it's a 0.96. What should our answer be? 0.96. So that's how you do that. Okay, so this is it for the notes. I'm going to post the homework on Canvas. Make sure that you print that out and work through those. If you have any questions, make sure that you join me for office hours or tutoring, and we will see you next time. Now, things aren't changing so much that I don't say make sure that you slap that like button right across that face. And make sure that you subscribe, because I think what I'm going to do for office hours is do YouTube Live. And so I'm only going to open it up to people that have subscribed. So make sure that you click that subscribe button. All right. See you later.